Good morning, Kansas City. Let's get ready to learn on KCPS Homeroom. I'm Justin Robinson, your homeroom instructor today. Today is Science Wednesday. Let's meet your elementary science teacher, Miss Tag.
Hi, scientists. My name is Jessica Power, and I'm one of the science curriculum coordinators at Kansas City Public Schools in Missouri. We're going to spend some time today talking about heat and energy, and specifically talking about the sun and how the sun affects the surface of the earth. But before we jump into talking about how the sun affects the surface of the earth, we're going to learn about different sources of heat and what heat is. So let's think about this. If I think about the word heat, I typically think about something being hot. Well, you're on the right track if you agree. The amount of heat something has tells us what temperature it is. The more heat in a substance or an object, the higher the temperature. The less heat in an object or substance, the lower the temperature. So let's talk about soup. On a cold winter day, soup helps to warm us up. Now, in order to make that soup hot, we do a couple of things. We either put it in the microwave to heat it up, or we put it on the stove. By turning on the stove, that creates heat from the stove that goes into the soup to make it hot. So the stove is a source of heat. It provides heat to make something hotter. What are some other things that could be like a stove that would cause temperatures to increase? Let's think about that. Do you have any ideas? If you said the sun, you are correct. And we're gonna look at what the sun does in just a little bit with some ice cubes. What are some other things? If you said the light bulb, you are correct. Let's take a look at an example of how a light bulb provides heat. So what I have here, this is called a wax burner, and it plugs into the wall with an electrical cord, and inside is a light bulb. Now this light bulb gets really warm because it has heat, and it causes this little tray to warm up as well. Now what people do sometimes is they take a piece of wax that has a scent in it, and they put it on top of the tray with the light bulb on it. Now the longer that this wax sits in the tray that's been heated by the light bulb, the wax begins to melt. And then what people do sometimes in their home is they allow this to fragrance or make their home smell good. I think this one I have here is like a clean, like a linen type of smell. Anyways, the whole point is that the light bulb is a source of heat to warm up the wax to melt it. We'll take a look at the wax burner in just a little bit. Keep a note, we have a solid piece of wax on top, okay? There's another thing that I know of that causes things to warm up, melt. It burns. Any ideas? A flame, that's correct. So let's take a look at a candle. So right here I have a candle. It's made of almost the same exact type of wax as what we put in our wax burner. Now a candle works by lighting it. So I'm gonna take my candle, take my lighter, and you can do this at home too if you wanna make observations. Just make sure you have your parent help you on lighting your candle. I'm gonna light the wick, part in the middle, and now we have a burning candle. Now over time, the wick is gonna burn down and it's gonna begin to melt the wax. Now why is this happening? Well, the flame acts as a source of heat. And as the wax gets warmer and warmer and warmer from more heat, the temperature increases. Now wax melts very easily. So when the wax melts, due to the heat from the flame, it'll turn into a liquid, and then that wax typically has some sort of fragrance, or you put them on a cake for your birthday and it melts. Don't want to eat the wax. It's difficult to see. It's extremely difficult, but you can see that wax is starting to drip right there. So that flame heats up that wax and begins to drip. We don't have a fire hazard. Okay, so we've talked about light bulbs being the source of heat for our wax burner. We've got a little bit of melting going on. We've talked about flames being a source of heat. We talked about stoves being a source of heat. And I said earlier that we would come back to the other source. Do you remember what that other source of heat was? That's right, it was the sun. Let's talk about the sun. The sun is a star in the middle of our solar system. So we live here on planet Earth, and the sun, we'll pretend that's my fist, the sun is in the middle of our solar system. And so as an Earth, we move around the sun. In a circular motion. Okay? Now the sun provides heat and light for us on Earth. So if you think about plants, plants need light in order to grow. If you've seen plants that maybe have turned wilted during the summer when it's really, really hot outside, that's because the sun, the energy from the sun, has evaporated the water inside the plant, and that's a sign that plants need more water. We're going to focus on how the sun warms up the surface of the Earth. So we have a couple demos that we're going to look at today. And the first one we're going to look at is what happens to the rate or the speed that an ice cube melts when it's put in the sun or when it's put in the shade. And what this demo is going to show us are the effects of sun's energy on Earth's surface. So let's break that down. We know the sun warms up different surfaces. If you've ever walked outside barefoot on a summer day, you probably noticed that the concrete or cement is really hot. I know I can't walk around barefoot on the cement. It hurts my feet too much. You also may have seen, like I said earlier, plants that have wilted because they need water. Or you might see plants that have actually burned in the heat. Not like a flame on fire, like our candle, but they actually get a sunburn and they start to crisp and turn brown. Sometimes they get white spots. Now the sun also provides rays, which we'll talk about even later, called UV rays, and that's what causes skin to change a darker color in the summer. And that's because of something in our skin called melanin. And that melanin makes our skin turn a darker color for protection. You've probably noticed that in the summertime, we actually see the sun in the sky longer than in the winter. So when you look outside, you'll probably notice that it's sunny when you wake up, and it's sunny when you go to bed. In the wintertime, it's typically dark when you wake up and dark when you go to bed. So the longer amount of time that the sun is in the sky actually allows the sun to provide more heat energy to us here on Earth. And so the surfaces or the items on Earth tend to warm up more than in the wintertime. Let's talk about the warming effects of the sun. So we talked a little bit about how when you walk outside, the concrete gets really, really hot and it hurts your feet. We talked about plants. Sometimes if it's hot enough, you can even cook an egg on the sidewalk. If you've seen videos down in Arizona where it gets to be extremely hot, or even here in Kansas City, on some summer days, it gets hot enough, above 95 degrees typically, that when the heat from the sun warms up the concrete itself gets up to be around 150 degrees Fahrenheit. That's warm enough to cook an egg. So you can lay a piece of foil out, just to be safe. Crack your egg on the foil, which is on the concrete, and over time, it will cook your egg. Yes, you can eat the egg, it's cooked. Okay, let's talk about our demos for today. We're not gonna cook an egg today. It's not actually hot enough in Kansas City. But we can see the effects of the sun's direct rays. Let's talk about what it means to be a direct ray. A direct ray means that the light is shining straight on an object. So it'll be sunny. Now, indirect means that there won't be light shining directly on the area. We also know that as shade. So we're going to compare how fast it takes an ice cube in the sun to melt compared to an ice cube in the shade. My prediction, or my hypothesis, is that the ice cube that sits in the sun, getting the direct sunlight, or more heat, is going to melt faster than the ice cube sitting in the shade, or getting indirect sun. I think that's going to happen because the surface that I put the ice cube on will be warmer due to the amount of direct heat than the surface that the ice cube is going to go on in the shade. So let's go take a look. Okay, scientists, so we're going to try our ice cube demonstration. I have a cup of ice cubes right here, and we're going to place one of these ice cubes into the sun, and we're going to place one of these ice cubes in the shade. So here's our ice cube in the sun, and here's our ice cube in the shade. So we're going to let these sit for a little bit. We're going to watch them melt. We're going to see which one melts faster. The one that's in the direct sun, in the sunny area, or the one that's in the shade, in the indirect sun area. It's hot outside. Okay, scientists, so we took a look at our ice cubes. We timed the ice cubes. We saw the ice cube in the sun did in fact melt faster than the ice cube that was in the shade. We proved our hypothesis to be correct. Now let's talk about something else the sun causes. I mentioned earlier that the sun causes our skin to tan. And that happens from something called ultraviolet rays. You may have heard the word violet. We know violet as a kind of purple color. But outside, you can't see these ultraviolet rays, but we know they're there because we can test for them. Now, ultraviolet rays come in two forms. There's ultraviolet A rays and ultraviolet B rays. And we can't see those rays. What we're gonna do is a second demo. I have these ultraviolet beads. And what happens is that when they are exposed to ultraviolet rays, they begin to turn a color. Let's take a look at what these beads look like. So I have these beads and they're actually wrapped up so that sun doesn't get exposed to them. Let's unwrap them. Okay. So here's what my ultraviolet beads look like. You can tell they're just a basic white bead. But when we take these out into the sunlight, they should begin to turn a color. Now that color is going to prove to us that there's ultraviolet rays or energy from the sun that we can't see, but affects these beads. Now think of these beads like skin. The darker these beads become, the more ultraviolet rays have been exposed to them, meaning the more energy or rays they've absorbed. Now, if we think about that like our skin, the darker our skin becomes, the more melanin, which is a chemical in our body that protects us from the sun, the more melanin our body has. And so the darker our skin becomes due to the ultraviolet rays. Now that poses a really good question. People get different colors of tan. And people also have different skin colors in many different places here on Earth. Well, that has everything to do with the melanin that I mentioned that starts to turn our skin darker in the sun. Think of melanin as a self-produced or human body created sunscreen. Melanin helps to protect our skin from damage. So people have came from all over the globe. They live in different places. People who live in places that are closer to the equator or areas that get way more sun, hotter temperatures, more sunlight throughout the year, typically have more melanin in their skin and typically have darker skin colors. Now, people who live farther from the equator, where there isn't as much sun exposure, typically have less melanin in their bodies and typically have lighter colored skin. So really, our skin color and the ability to tan, it has everything to do with the melanin inside of our body, where we or our ancestors are from, and the sun. So let's go take a look at what happens when we put these ultraviolet beads in the sun. Do you think they're going to become a light color with a little bit of ultraviolet ray being absorbed? Or do you think they're going to get a dark color, meaning lots and lots of ultraviolet rays are absorbed? Make your hypothesis right now, and we'll go outside and see what happens. So we have found a sunny place on some concrete, and I have the solar beads in my hand. What I'm going to do is drop these on the ground. You can see that red one automatically changed colors. Okay, scientists, so we're back inside after testing out the ice cubes and after testing out the solar beads. We found that the ice cube in the sun melted faster than the ice cube in the shade. And we can say that's because the sun causes the direct heat to go to the ice cube and melt faster than the ice cube that's in the shade getting the indirect sun. For our solar beads, you saw the moment they were put in the sun, they immediately started changing to different colors. There was red and green and yellow and blue. Now, the longer those colors sat in the sun, the little bit darker they appeared to get. And we connected that to the melanin in our skin. So keep in mind, all around us are different sources of heat. And heat causes different objects and substances to increase in temperature. At the very beginning of this video, we talked about the wax burner and how the light bulb was a heat source for the cube of wax that we put inside the tray. Let's take a look at that. So here's our wax burner. And it has gotten very, very, very hot. And you will see, scroll down a little bit, that now, instead of just a ball of wax, we have a little bit. You'll see that that wax has turned into a liquid. And that liquid now is then fragranting or causing the room to smell like clean laundry. So again, just another example of how sources of heat can cause the temperature of an object to increase. And that then makes that wax, as our example, melt. So, the next time you're outside, take a look, walk on the grass, compare the grass, how hot the grass is to how hot the concrete is. Take a look at what happens when you leave a rock or, I don't know, you leave a candy bar outside. See what happens when you expose different objects to heat. Do they melt? Do they get softer? Do they freeze? I think there's another reason that happens. You take a look for yourself. Thank you for watching and have a great day. My name is Jessica Power, and I'm one of the science curriculum coordinators with Kansas City Public Schools in Missouri. We're going to spend some time today talking about energy, what energy is, the different types of energy, and then how we can go from one form of energy to another. And in fact, we're going to do that by cooking s'mores in a solar oven that you can make at home on your own, but maybe with a little bit of parent or guardian support. So let's get started. First things first, energy. What is energy? It's all around us. We use it all the time, and we most of the time need it. In fact, every time we eat food, that's energy that our body needs to keep us alive. Energy is the ability to cause change or do work. So let's focus on just that cause change for today. When we talk about energy causing change, the easiest one to think about is temperature. Even easier is to think about the sun. We know that the sun is a star, very, very far away in the sky. It's the center of our solar system, and we use the sun, or the sun provides us, energy and light that we need, right? So plants need energy. Plants absorb that sunlight And they use it to make what's called glucose, or food, for them to survive. And then as the food chain continues, we eat those plants, or we eat animals that have eaten those plants, and then we obtain that glucose, or that sugar, that energy that the sun provided to the plants. That then goes to our bodies. So let's talk about energy some more. We're going to focus on the sun today. We're going to focus on the sun's ability to go from thermal, or heat energy, and transfer that to cook a s'more. So we're gonna go from solar light energy, thermal energy, and that solar energy is gonna go into a solar oven that I've already created and I'm gonna show you. Very excited about it. And then it's gonna warm up the graham crackers and the marshmallows and melt the chocolate. So in a sense, it's cooking or providing heat energy to melt all of the gooiness and the sugar of our s'mores. So let's go back to our definition. Energy is the ability to do work or cause change. So we're going to focus back on the sun again. When the sun shines down on us, it causes the things around us to warm up. Think about cement on a hot summer day. Sometimes when you go outside and walk around barefoot on cement, it really hurts and it can burn your feet. And that's because the sun has taken its light energy, its thermal energy. The concrete in the cement has absorbed that energy, causing an increase in temperature change. That's basically what we're going to do with our s'mores today. Now let's rewind real quick, because energy is more than making s'mores and the sun. There's different forms of energy. Some of those forms include sound, they include light, they include motion, they include heat or thermal, they include electricity, they include nuclear. Maybe you've heard of nuclear energy. That's a little bit more advanced than what we're talking about today though. So let's get down to business with our solar oven. So for our solar oven, you can make one of these at home as well. All you need is a shoebox or some sort of box that you can cut a flap into. For your box, you're gonna cut a flap 1 inch around the perimeter, but you're gonna wanna leave that flap so that we can open and close it. Next, you're gonna line the inside of your box on all sides with aluminum foil. I use clear tape to help tape down the foil so it stayed. You could use glue, or you don't really need to use anything if you don't want to. Next, I made sure that the lid, or the flap here, was also covered in aluminum foil, because that's gonna help to reflect the light that's gonna cause the heat and the temperature to increase inside of our oven. Last, I put just a clear piece of plastic wrap or cellophane, whatever you call it, over the box. So here's how this breakdown works. We're gonna set this solar oven, into the sun. The sun is gonna shine down and it's gonna provide it with solar energy, thermal light energy. That light energy is going to be reflected and trapped inside of this oven. Now our cardboard, the actual box itself, and the clear plastic on top is going to act as an insulator, and it's going to help trap all that light energy. And the more light energy that we attract and we contain or keep inside this box, the hotter the inside of the box is going to get. Now, the hotter the box gets, the warmer the things that are inside of it are going to get as well. So we're going to stick this outside. We're going to let it preheat. You know how you turn the oven on, you hit preheat and it warms up to whatever degree you need it? We're just gonna set this in the sun and let it preheat. Then, once it preheats, we're gonna stick a graham cracker, a marshmallow, and a piece of chocolate inside. And we're gonna create s'mores, not even having to go into the kitchen. So, again, to make one of these solar ovens, you're first gonna find a box, shoebox. Works great. I found just a box laying around at home that had a bunch of science stuff in it. You're gonna cut a flap about 1 inch from the perimeter of the box. Then you're going to cover the inside of your solar oven with foil. Again, I taped my foil down. You do not have to if you don't want to. Lastly, I put a piece of clear plastic wrap over the top, over this hole. Now I have mine loose. You can kind of see that. That way I can still get inside of the oven. So I'm still able to put things inside of it, and then I can just peel back that plastic wrap to help insulate it. Okay? I will see you outside. Okay, scientists, so you can see that we've placed our box outside in the sun. We've got the sun shining down, and those rays are going to reflect inside of our solar oven. You'll notice I have the flap open just a little bit to allow the sun's rays to get into the box. Those rays are then going to increase the internal temperature of our box. So we're going to come back in about 15-20 minutes. We'll put our graham cracker, we'll put our marshmallow, we'll put our chocolate inside the box, and we'll cook our s'more. Okay, scientists, we're back and we've let our solar oven heat up to a very warm temperature. I went ahead and just pulled that plastic wrap back a little bit. That way we could get the plate with the marshmallows inside. Now you'll notice I didn't put chocolate in here. It is way too hot outside today. So if we were gonna put chocolate in those, that chocolate would melt way before these marshmallows warm up. So we're gonna go ahead and you'll notice just to make things a little less messy, I put some, I just have a paper plate and some aluminum foil. We're gonna go ahead and slip this into the solar oven. Hopefully we don't lose a marshmallow. Okay. We're gonna pull our plastic wrap back so it helps insulate. And we're gonna let our oven sit with our marshmallows and we'll come back when they're cooked. All right, scientists, we're back. We can see some changes happening with our marshmallows. I'm gonna peel back the plastic a little bit. We can poke at it. Woo! See that? Our marshmallow is getting really gooey. Can you see how soft the marshmallow is? It's pulling up sugar on my finger. So we're gonna take these back inside. I'm gonna go ahead and put some chocolate on top of it, enjoy these s'mores, and we will come right back. All right, scientists, so we made our solar oven. We watched and we saw how the marshmallows started to get gooey from the internal temperature of the solar oven increasing due to the energy from the sun that then transformed from solar energy into our heat energy, which increased the temperature of the solar oven. All right, scientists, let's do some recapping. We first started out talking about energy. We decided that energy's definition is the ability to do work or cause change. We spent our time today focusing on that last part, the causing change. We talked then about the different forms of energy and how energy can be in different types. Just like there's different types of shoes, there's different types of energy. There's sound energy and light energy and thermal energy and solar energy and nuclear energy. Oh, we could just keep going. And mechanical energy, and we'll worry about that later. The point is that with all the different kinds of energy around us, they don't just stay in that one form of energy. They transfer or convert from one form to another. So today's example with the solar oven is we went from solar energy and we transferred that into heat energy. We're able to take energy from the sun, right? Those radiation rays, that light energy. We were able to capture that inside of our solar energy box in order to increase the temperature of our solar oven to make our s'mores. There's other ways to transform energy. If you think about, like we talked about earlier, flipping on a light switch, that's nothing more than a circuit. There's stored energy. That's once the light switch is turned on, that energy then travels through the wires in your house or any building, and then allows you to have light energy, which allows us to see. Same thing with TVs, same thing with computers. There's a reason you have to plug in a cell phone in order to get a charge. You take energy that comes from the outlets, that electrical energy, and that then is turned into a different form of energy that allows us to use our phones or computers. When you think about riding in a car, we have to put gasoline in our vehicles. And that gasoline, once we turn our vehicle on, gets changed into a form of energy that allows the vehicle to go. There's so many different forms of energy, but we just focused on a really simple one today that allowed us to use our solar oven. If you're interested in more ways to learn how energy impacts you in the areas, the different types of energy, feel free to do some research on your own. Feel free to try to contact your local electricity company. Feel free to do some investigating. You can always make a solar oven on your own. If you have the ability to get some wires and a light bulb, you can try to make your own circuit to convert energy. The whole point is that we need energy. We rely on energy around us, and we need energy to survive in the form of food. Not too much food. S'mores aren't good energy, but you know what I mean. So be looking out around you. Where do you see energy? Where does energy come from? Where are places that energy transforms from one place to another in your home or in the world around you? I hope you enjoyed talking about energy transformation. Go make your solar oven, enjoy some s'mores, whatever you want to cook in there, pizza, mac and cheese, you name it. Have a great day.
Thank you, Miss Tag. We'll see you next week. And now for your secondary science lesson, here's Dr. Phil Jones.
Good morning, ladies and gentlemen. I'm Dr. Jones. I'm the science coordinator for Kansas City Public Schools. And today I'm talking specifically to my middle school students. And we're going to be talking about the structure of chemical reactions. Now, understand, when we talk about chemical reactions in middle school, what we're really talking about is what happens before and after an event, or before and after a reaction takes place. Now, before we get into this whole discussion, well, what really is a chemical reaction? Think of it this way. A chemical reaction is when you start out with a certain something we call a reactant, and then due to change, it's rearranged, reorganized to become something different, which would be a product. So in this case, if you notice, the gas went from being that yellowish color to this red color, and that red color lets you know that you have a new product that you didn't have before. Now, when you're looking at matter, you can describe it in two different ways. You can either talk about its physical characteristics or its chemical characteristics. So let's begin with physical characteristics. What are they? So volume, mass, melting point, boiling point, these are the types of things that you can physically see. But more important, size, shape, weight, density. These are things that, again, you can describe something. I always tell people, when you think about physical properties, think about the way that you meet someone. And you can notice like what they're wearing, or the way that their hair is styled, or something of that nature. Chemical properties are what's inside, okay? Again, similar to people. So, for example, reactivity with other chemicals. I have two children. My son, he's older, he's in high school. If you put him in a group of strangers, he will immediately start to introduce himself. He's very, very open. He's very easy to approach. My daughter's in middle school. She is completely the opposite. If you put her in a group of people that she doesn't know, she will literally just cocoon herself. So you see that just like with chemicals, people, depending on what's inside, can either react with a new group or be very, very distant and restrained from a new group. Toxicity. Now, I know that you've seen this image sometimes following trucks, and really this image tells you about the chemical properties inside a vehicle. When we talking about toxicity, you're talking about doing harm. And I do know that you probably have a few friends that you already know. They are kind of toxic. They're the ones that talk about people. They're the ones that post, things that you really wouldn't want to say in a group of folks. In addition to that, flammability. There are certain compounds and chemicals that will immediately ignite. And again, I know you have some friends that it doesn't take a lot to just set them off. And then lastly, the oxidation state. These are things that will rust. And so what you find is that if we compare it to people, you have some people that cannot take the pressures of life, or if something is not perfect, they can't, weather the storm. So, in a lot of ways, these are internal characteristics or internal properties of matter, where again, these are external on the outside, physical. Now, let's talk about the difference between physical and chemical change. So, for example, this is Destiny's Child from 1990. Now, if you recall, in 2000, there was a switch. And if you notice, here's Destiny's Child from 2000. Now, these two folks stayed the same, but where did they go? All right? Here's another example. Little Yachty. Little Yachty and his Ferrari. Nice car. That was pre-crash. Here's the car post-crash. So you can tell there is a change here. And my favorite, this is Justin Bieber. Justin Bieber before Selena Gomez. Well, here's Justin Bieber after Haley Baldwin. And if you notice, This little guy, yeah, you could easily come into my house. Hey, you could date my daughter. This dude wouldn't let him walk my dog. I'm just saying, rough life. But the whole point is this. Some changes you can reverse, some you can't. So let's talk about characteristics between physical changes and our chemical changes. So let's start with the first one, up top. Physical changes that occur will not change the composition of matter, whereas a chemical change will. So again, let's look at Justin. Justin Bieber before, Justin Bieber after, it's the same guy. We haven't really changed who he is internally, but there's some external differences. However, if you look at the composition of Destiny's Child, they did change. So in this case, this would be like a chemical reaction because we physically changed the composition. We took two people out, added one new person. Okay? Another one deals with reversibility. Physical changes can be reversed. Chemical changes are irreversible. They can't be reversed. Now, as much as Justin may want to go back to this kid, not going to happen. However, let's say these two decide, you know what? I'm not doing anything post-COVID. Hey, let's get a Destiny Child 1990 reunion concert going. Well, she's still around. And she's still around too. Notice, you could actually go back to the 1990 version of Destiny's Child. Now, new products being formed. Now, this is very important, and here's why. Although this car cannot be driven, technically, everything that was on the car before the accident could be found somewhere on the street after the accident. It didn't really make anything new. Now, yeah, I know the airbag went off, but let's not, split hairs here, okay? Now, let's talk about how it reacts to environmental changes or changes in heating and cooling. These are ice cubes in the sun. No problem. They melt, keep your drink cold. This is ice cube in the sun. Here's the difference. If you notice, that's that same look that your dad would give you anytime he said cut the grass, and you were like, okay, and then you went out and played with your friends, and then you came back, and that dude opened up the door. Yeah, you don't want that. This is a snowball. I come from New Orleans, Louisiana, and this is a frozen drink. All we do is take some ice, put a little juice on top, great dessert. Cool you off, wonderful. This is also a snowball, but this is the snowball from Animal Farm. And I will tell you, if you put that in a cold place, he would probably start shivering and things of that nature. So if you notice, when we're talking about chemical and physical changes, yes, a physical change will change the state, but you don't have all these other reactions going on, especially absorbing and releasing energy. Now, next, when we talk about bonds being formed, well, here's one thing I want to show you. When you heat water, right? And again, we're talking about just putting it on the stove. You can boil this water all day and night. You're not going to make any new bonds. Steam, liquid water, and ice, still water. However, if you take an egg and put it in that water, all right, what will happen is you'll start changing the composition of the actual proteins. You'll rearrange them. You do the same thing when you put lye or you put a permanent in your hair. So anytime you chemically alter your hair, you're changing those proteins, just like when you add heat to an egg, okay? And trust, once that happens, you're not going back to this egg, okay? Now, let's talk about signs of chemical reactions. And this is the most important part of this because you're going to need to know how to tell if a reaction has taken place. So the first thing, color change. I like Sammy. This is my boy Sammy. Sammy before, Sammy after. Now, here's the thing about Sammy. I don't care what Michael Jackson or Uncle Ruckus says. That is not reverse vitiligo. That, my friend, is what happens when you put bleach on your skin. All right? Next, formation of bubbles and gas. Now, here's the thing. Everybody knows about Mentos and Coke. This is great. This is wonderful. Here's the thing about that. They're outside. Here's why that's important. If you try this inside, then you got to meet this dude, which you don't want to do. So remember, Mentos and Coke outside, not inside, or you get ice cube in the sun. All right. Changes in odors. I know. The cow, yes. But again, that is also a chemical reaction. Yes, passing gas is a chemical reaction. Formation of particulates. Now, when I say particulates, some people get it confused with like rain. No. Here's what we're talking about. You ever had juice that's been in the refrigerator for a while and you kind of swirl it around and you see these things kind of floating in it? All right? Yeah, things have happened. You also find in chemistry that you can take two things that are clear, put them together, and you'll get stuff like this. That's a reaction. So this is something that happened when I added the two chemicals together. Changes in temperature. Hot hands and cold packs, both of which are caused by a chemical reaction. And then the last one for all of you Halloween fans, the glow stick. If you ever had a glow stick, until you go crack and open it up, it will not illuminate. But once you do that, it will glow until the reaction stops. Sometimes 6 hours, 8 hours later, your glow stick is still glowing in your room. Yes. So, all in all, here's the take-home message. First of all, chemical reactions will change your reactant, what you started out with, to a product, something completely different. You can tell that a chemical reaction has occurred if one of these or multiple of these occur. And, more important, not all reactions are chemical reactions. Some of them are just physical changes, like melting melting ice and forming water, or boiling water and making steam. I hope this helps you out, and next time I'll actually show you some reactions where this is taking place. Thank you. Good morning, ladies and gentlemen. This is Dr. Jones. I am the science coordinator for Kansas City Public Schools, and today I want to talk to my high school students specifically about acids and bases. Now, I know for most of you guys, you're either taking bio or you're taking physical science, and you're like, why do I need to know about acids and bases? Well, part of the reason is because acids and bases affect all aspects of our life. Now, when we look at the standard as far as, what the state wants you to understand, when we talk about an equilibrium, what we're talking about is a balance. So there's a lot of reactions that occur in biology, in physical science, and in chemistry where you have two sides that are connected with each other. So as one goes up, the other one goes down, and vice versa. Well, acids and bases are just like that. In that, you have this OH group, hydroxide ion, and then you have your H+, your hydronium. And what you find is that these two are in constant struggle between each other, in that if one goes up, the other one goes down, and vice versa. So, let's talk about pH, all right? Because most of you are familiar with pH, and the pH scale really says how many H+ ions do I have, are available, okay? Acids tend to have a lot of these, whereas a base doesn't. So if you're looking at this scale, if you're on this side, you would have a lot, whereas if you're on this side, you would have, very few of those hydrogen ions. Now, here's the deal. If you're looking at your numbers, you're like, wait a minute. You're saying I have more H+ if I have 0 for a pH than if I have 14? Yes, and we'll get into that in a second. Now, if you look at the fact that, again, we're talking about a balance here. So there is an alternative scale, almost like a bizarro world version of pH. It's called POH. And with POH in this bizarro world, as you say, you find that you would have a lot of OH minus ions. So in that case, now something that's a base would be 0, but something that is an acid would be 14. Okay? Now, when we're looking at this in its totality, okay, what we're saying is if you're a base, you have a lot of OH minus, very little H plus. If you're an acid, you have a lot of H plus, but very little OH minus. So why do we keep on talking about H plus and OH minus? The main reason is because of water. If you look at water, it can either be an acid or a base, and here's why. Water is H2O, which means it has OH and H plus in equal amounts. So think of water as being right here on your scale, okay? And that is what really helps guide this whole discussion. Think about it like this. If you get soap in your eyes, and soap is a base, what do you put in to get the soap out of your eyes? Water. If you get lemon juice in your eyes, which is an acid, what do you flush your eyes out with to get rid of the lemon juice? Water. And that's because water will make a base act more like an acid, but water can also make an acid act more like a base. Okay? Now, when we're looking at this idea of an aqueous solution, we're talking about just a solution that has water plus something else, okay? There is a way of figuring out exactly how many of these H plus and these OH minus ions we have present, okay? Now, this is where math comes into play. Now, I know some of you are saying, wait a minute, wait. Aren't we talking about science? Well, all of that algebra that you learned in like 9th grade, now it's coming back around. And it's going to come back around in 11th grade, and it's going to come back around in 12th grade. But for this purpose, we're talking about this thing called KW. Think of KW as a way of describing water in equal amounts. So we have the H3O plus, which is for us, H plus, and then we have this OH minus. So we're saying if I have equal amounts of H plus and equal amounts of OH minus, I should get 1.0 times 10 to the 14. Now, here's where that 14 number comes into play. If I'm looking at this, okay, and saying, okay, what does this have to do with the scale? Well, if we go back and we look at this, notice 10 to the 14, 14. This 10 to the minus 14 means I have a 1, and then I have 13 zeros, and then the decimal point. So that number is very, very small. However, if you have something to the first power, like 0 to the, or 10 to the 0th power, that's 1. So again, if you're looking at this, these numbers actually represent exponents. This being 10 to the 0th power, negative 1, negative 2, negative 3, negative 4, all the way to a negative 14. Now, again, don't get caught up on that as much as the fact that just realize that as this number gets bigger, my amount actually gets smaller, okay? That's why something that has a pH of, let's say, 10 has less hydrogen ions than something that has a pH of 1. Because this technically is 10 to the minus 10, whereas this is 10 to the minus 1. All right? Okay, now, let's look at one of our problems. So, for example, if I know one side of this, which would be like the OH side, I could calculate the H plus side. Here's how. All right? And this is kind of, again, where this algebra comes into play. If you recall from algebra, if you have something on one side of the equation and you divide it by both sides, you can technically move a number over. So in this case, here's what I'm doing. I said, okay, we have 3.4 times 10 to the minus 5. All right, great, wonderful. That number on this little equation is right here. I know that 10 to the 14, that's that magical number that represents water on both sides. If I divide this, that'll give me this quantity or this number on this side, okay? And so really all you're doing is you're just taking whatever number you get here and you're dividing that into your 1 times 10 to the minus 14 number. It's That simple. A lot of times people get caught up on the whole thing about pH because you have an exponent. But really, it's not that difficult. Okay? Look at this. I have the hydrogen ion, H+. We're looking for the OH. Again, all I have to do is just take the number that they gave me and divide it into 1.0 times 10 to the minus 14. That's simple. All right. So now that we have the hydrogen ion concentration, what is that saying? Or the OH concentration, what is that saying? Well, if I have a number that is higher or smaller than, let's say, 10 to the minus 7, then that lets you know that you're going to be on the higher end of the scale. So, for example, notice, hydrogen ion number, right? H+, 10 to the minus 12, which means this thing is actually going to be a base. If we go back to this one, notice this has a H+ number of 10 to the minus 5. So think of this thing as being like an acid, all right? So let's talk about exponents, all right? So first of all, let's say we have 10 to the 0th power, all right? And let that be like the ground floor. So here we are on the ground floor. Now, if we want to go upstairs, meaning we're going to increase this by 10, that would be going up one floor, or 10 to the first power. If we go up 2 floors, and let's say now we're at 100, that would be 10 to the second. Well, the same thing with pH, but we're going down. So now we're saying to go down, this would be 10 to the minus 1, which is 0.01. All right? If we go down 2 levels, minus 2, that would be 0.01. So when we're looking at pH and we're looking at these numbers, when you have a 0, think of a 0 as being 10 to the 0th power, or the same thing as equaling 1. When we go 14, think of that as being 10 to the minus 14, which would be the same thing as saying 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13.0. All right? So you can see this number is very small compared to 1. Okay? So that's why 10 to the 0, or a pH of 0, is a lot bigger than a pH of 14. All right? Back to the presentation. So, now that we've established that, now let's start talking about how do we calculate these things. Because again, now that we know what concentration means, now we have to figure out, okay, how do I take that information and decide whether I'm messing with vinegar or Coke, or whether I'm messing with something like Drano. So water has this property of having both OH and H+, okay? And we call this equilibrium Kw, all right? Now, again, looking back at what we had before, going back to our annotation, why is Kw so important? Here's why. Well, if I'm looking at this and I say, okay, water has just as many H+ as OH-, then what we're saying is if I take and add the concentration of H+ and the concentration of OH-, I'm going to get this little balance, this scale that technically will have on both sides equal amounts of my two ions. That number is equal to 1 times 10 to the minus 14. All right? Now, I know this is a lot of math going on here, but it's not that hard. Here's why. Let's say if this was C, this was A, and this was B. If I'm trying to find A, we could say A equals C divided by B. If I want to find B, we could say B equals C divided by A. So, if I know any one of these two, I could figure out the other. That's one reason why water is so important, but that is also why when we start talking about concentrations, we can just focus on this side and get an idea of what this side is. That's why pH is important, but pOH, not so much. So let me give you a problem. First of all, let's assume, that we have a solution that has a hydrogen plus, H plus concentration equaling 3.4 times 10 to the minus 5. Okay? Now, again, remember, 1 times 10 to the minus 14 equals whatever this concentration is for H plus times whatever the concentration is for OH minus. This number goes here. So when we look at the math here, all we have to do is plug in and substitute. Here's what I mean. So we have 1.0 times 10 to the minus 14. That's our KW number, right? That's that number that we say is kind of like water, where you have equal on both sides. Now, that would equal 3.4 times 10 to the minus 5. So that's what was given in our problem. We're trying to find OH minus. Okay? So if we divide both sides by this number, then what we're left with is just our OH minus concentration. And this is going to actually give you a OH minus concentration of, hopefully you have your calculators, 2.9 times 10 to the minus 10. Now, here's the question. Which number's bigger? Is this bigger or is this bigger? Well, remember what we said. When we're looking at our exponents, this is technically like saying 0, 1, 2, 3, 4, and then a 1. This is like saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then a 1. So who's bigger? This is. And so in this case, this would be an acid. Now, when we come back next time, I'm going to show you how to take this and then calculate pH. Because that's the number that you see on jars, on canisters, and that's the one that you really want. Because this is the one that is low for acids and high for bases. See you next time.
Thank you, Dr. Jones, and thank you all for joining us. Tomorrow is Social Studies Thursday. We will see you then, and students, remember, keep learning throughout the day.